We would now like to explore a property of work done by forces called path independence. So recall that our work is defined to be an integral of f dot ds from some initial to some final point. Let's look at an example. The force that we're going to look at is the gravitational force. And let's draw a coordinate system. Let's take an initial point and a final point. And let's choose plus x and plus y, and our unit vectors I hat and j hat. And in this example, we're going to consider the gravitational force near the surface of the Earth, which is constant, pointing downwards. And what I'd like to do is consider two paths. I'd like to consider a path that first path goes straight up and over. So this will be path 1. It has two legs. And the second path, path 2, will go horizontal and vertical. So that's going to be path 2, and it has two different legs. And we'd like to evaluate this integral on both paths. Now, the way we do that is, first off, let's start with path 1. We'll call this y initial, and we'll call that y final. And we'll draw the gravitational force, mg on both legs. And now we see that when we do the integral along this first leg of path 1, the gravitational force is opposite the direction we're moving, the displacement. So the integral will be negative. The force is constant. And so the work done is simply minus mg times delta y, which is y final minus y initial on that first part. Now on the second part, this is a right angle. And because it's a right angle, the dot product is 0. So that's the total work done on path 1. Now on path 2, well, again, let's just draw our forces. We have gravity down, and we have gravity down. And we can see that once again, on the first horizontal leg of path 2, this integral is 0 because it's moving perpendicular to the force, the direction of this along the path. And on this leg, just as on that leg there, the gravitational force is down, the integral is negative. We get exactly the same result. Now what we'd like to do is consider a more general path rather than these two horizontal and vertical legs. So let's draw a coordinate system again. Let's introduce I, and let's introduce f plus y and plus x. And now let's consider a path which is moving like that. Now on this path, what we want to do is break it down into horizontal and vertical pieces. Horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical. And let's focus on one of these pieces, which has a displacement ds going from one point to another. Now, if we blow that up, so we have our displacement ds, then what we have here is a displacement dx in the horizontal direction and dy in the vertical direction. And so we see again that when we compute this work and our gravitational force is downward, then the horizontal part of this displacement, the dot product in the horizontal direction, 0, only the vertical part cancels. And so when we add up the work along these horizontal and vertical pieces, only the vertical piece counts. We're just adding up the dy's until we get y final minus y initial. Now let's be a little more analytic here and write out our ds as a vector dx I hat plus dy j hat, and our gravitational force as minus mg j hat. Now the work is the integral from the initial to the final place of fg dot ds. And so when we do that, we have minus mg j hat dot dx I hat plus dy j hat, and from our initial to the final place. And notice that we have j hat dot I hat. They are perpendicular, so that dot product is 0. And j hat dot j hat is 1. And so what we're left with here in the integral is simply now we're integrating from y initial to y final. because we only have minus mg dy. And that's what we said before. Only the vertical parts are adding up. And so when you do this integral, mg is a constant, we get mg times y final minus y initial, and that agrees with what we had before. So this type of force is an illustration of a force where the work done is independent of the path we choose from the initial to the final place. Let's now explore an example of a force in which the work done is not path independent. And the classic example is the friction force. So let's consider the following setup. Suppose we have a horizontal surface with friction, and we have an object, and we're moving this object. So let's choose an origin. We'll call this plus x, our I hat direction. It's all going to be one-dimensional motion. And we're going to move this object from an initial to a final state, and we're going to move it directly in a straight line from the initial to the final state. And this will be our path 1. And in our second case, what we'd like to contrast with that is that we'd like to move the object out to a point xa and then back to the final point. So this is our path 2, has 2 legs, and we'd like to compare the work done on these 2 paths. So for path 1, we'll begin by calculating. Our force here is the kinetic friction force. And the kinetic friction force, remember, is, in this case, it's going to oppose the motion. So we have force kinetic for path 1, and that is minus mu k mg in the I hat direction. And so when we do the integral for the work from x initial to x final, this is path 1, then we have minus mu k mg I hat dotted into, now what is the ds for this path? It's simply dx I hat. So dx I hat. Notice we're not putting any sign into dx. That's the sign will show up in terms of our endpoints of our integral. So when we do the dot product here, we have I hat dot I hat. That's 1. And so this integral, we can pull out all the constants, mu k mg. We're just integrating dx from x initial to x final. And so we get mu k mg times x final minus x initial. Now, for path 2, we have 2 separate integrals. So for path 2, we'll just show the first part, where we're going from x initial to xa. Then the friction force is opposing the motion. And we always just write dx in terms of the coordinate system, dx I hat, because you'll see that the signs show up in the endpoints of the integral. And then when we're coming back, I'll put that in a different color, and I'll put it below it. So when we come back, notice the friction force is going to change direction. ds will still be written that way, but pay close attention to the endpoints of the integral. So now what we have is 2 integrals. So w is the integral from x initial to xa. And now I'm going to take the dot products here directly. It's the same friction force. We still have this same integral, which is minus mu k mg dx. Now, here's where it's a little bit tricky. Notice on this path, fk is plus mu k mg I hat. And so when we dot it into dx, we have a plus sign. We'll just continue that integration here of mu k mg dx from xa to x final. Both of these integrals are straightforward integrals to do. This is minus mu k mg xa minus x initial. And over here, we have a plus mu k mg x final minus x initial. Notice x final minus xa rather is negative. And so both of these integrals are negative as we expect. And so what we see here is that we have 2 pieces. So minus 2 mu k mg xa, and then we have that other piece, mu k mg x final minus x initial. Hang on, this is actually a plus sign. So our answer is very different because the amount that we've traveled is different. So what we see here is an example of a force which is the work done is not path independent, but depends on the path taken from the initial to the final states.